Today's Friday, so I don't have to finish on time, but I will. Okay. So today we're going to do error correcting codes. Uh, this is an important topic. Always a lecture that I feel like I'm kind of awkward about, but it's okay. So, uh, besides this application of error correcting codes, I'm going to use it to introduce this notion of entropy, which is also a very basic thing. Does anyone here work on error correcting codes? We have people who do coding theory, so guess not until homework. Okay. Um, so, so you have two people, person A and person B, and, and they're talking to each other, right? I always imagine like I always saw this as a kid, like supposedly you could take two plastic cups and like tie it with a rope and then like you and like the friend next door neighbor can like talk to each other through the window. But like I didn't have friends next door to my house, so I never really got to try out this plastic cup and a string. And okay, now so as you talk in your plastic cup, you say something, which is an M bit string, I guess, and then the other person, your imaginary friend on the other house, receives a message, right? But the problem is that plastic cones and wire and string isn't like super great technology, so some of the noise gets muffled uh, from here to there, right? So it's like, okay, you have this sort of, very primitive communication device. How can I actually communicate something meaningful? So you guys have probably been in this situation before. You're driving in between Indiana Police and Purdue, and there's some awkward dead zones in the cell phone coverage, and your cell phone call isn't quite going through, right? So you're like, yada, yada, yada. And then the person's like, I don't understand you. So what do you do? You repeat yourself. And you say, I don't understand you. And then you repeat yourself, and eventually you're like yelling, right? So, so you know that even with faulty communication, just by repeating yourself, oh, you can eventually get your message across, right? Or me talking to a sufficiently old relative, even with perfect cell phone connection, I just repeat myself until they agree. Or maybe that's how I teach. So uh, that's the high level idea. So we're going to look at a probabilistic model where as you send 100 bits, every bit is going to get flipped with some fixed independent probability p. Okay. And we get to design a coding scheme. So I'll take the original message and I'll encode it. Like maybe I'll just repeat the message 5 times. Okay. And then that'll become probably a longer message because it has some redundancy built in. It'll get sent over the string. Some bits will flip. So your grandmother gets a slightly garbled message, and then you're going to decode it. Right? So again, if you just like repeat your message 5 times for each bit, you can just take a majority vote, majority vote, majority vote. And that's going to be okay. It's better than nothing, right? So that would be like sort of a reasonable solution, but the real goal is to try to have as little overhead as possible while still maintaining some probability of success. So, right, so it's error correction. So formally, I guess here's a notation I'll use. I'll use C for encoder, I'll use D for decoder, and N for noise. So noise is a random function, not to be confused with like hash functions were randomly constructed functions, but once constructed were deterministic. This is really like a random function where x goes in and some random perturbation of x goes out. Okay? And so compactly the full communication would be like encode, noise, decode. So it'll kind of look like this, and I want to recover the original message. Okay. All right, so yeah. Well, so yeah, so good question. Why does the number of bits change, and should it go up or should it go down? I'll ask all of you. So M is the input, what I start with. N is what I send over the wire. So as I go from M to N, should it go up or down? Up. So I'm probably going to add redundancy. If it went down, then I'm just losing information. I can't possibly recover it. So like repeating a few times is going to be 3 times longer or something. Okay. So diagrammatically, you're going to take every input here and map it to some point in this bigger space if you've added some bits. Okay. Your decoder function, so at some level this is, yeah, 1-to-1, probably not going to be any conflicts. You're probably going to choose your coding thing so that you don't map this different words to the same one, right? And this space is much bigger. There's plenty of space. On the flip side, anything here should be decoded to some message over here. So, as far as like, oh, if I look at all the messages that or codes that get mapped back to Y, this is going to be a set of points. Okay, so this is just comparing the cardinalities. Okay, so yeah, here's a prettier version. Yeah. Well, D in general is just mapping big code words back to original smaller messages. So, so there's going to be collisions just from bigger set mapping to smaller set. And so, yeah, I'm just kind of drawing a picture to kind of reinforce the general relationship between the two. So many different messages are going to map back to Y, which is kind of what you want, right? You have Y, you're going to put it into a code. Some small bits will change, and you're hoping that the slightly changed version will still be able to map back to Y when I decode it. So you're hoping if Y is like, if it was actually a geometrically representative picture, you want Y to map right in the middle or something, so it has this region around which you can make mistakes. Okay. Good. Good. So, so here are the two quantities we're looking at. So in your scheme, you're probably going to have more output bits. Your encoded words will be longer than your input, but you want this to be as close to 1 as possible. So when I said smaller equals better, I should have wrote bigger equals better because that would be correct. Okay, so you want this ratio to be close to 1. So this one should be bigger. But this one, the average error rate, which I guess can be expressed compactly as the probability over, so this is a specific sense of the word average. So first there's some randomness coming from the noise, but then when we say average over all inputs. Okay, so if I choose a random input X and I apply the random noise, what are the odds that I ultimately decode the original message? So it's average over noise and input messages. Yeah. Yeah, there should be 0, 1 to the M. Okay. Overall, 0, 1 to the M. In the homework, you're going to be asked to make this a little bit stronger and come up with a code that for all X, the error will be small. Okay, it's actually not that bad. It'll build off what we do today, but we'll look at this more relaxed notion of error. Okay, so good. Good. Okay, so maybe what I want to point out is that, okay, by now you might know that this is a big field, but like once upon a time, this was just like a practical problem, right? AT&T is just connecting the country with wires, and they're, sending messages, telegrams, whatever, right? And bits are getting flipped, and they're just trying to come up with something better than just like buying more and more expensive metal that makes less mistakes. Okay, we're looking for like a software solution to compensate for mediocre hardware. So this is like the 1940s or something, right? So we're gonna Okay, so at some level, it's not even clear that like this is even like a very fundamental question. This is just like a mechanical question, right? Like how do you fix your toaster or something? It's not clear that something very clean is going to come out at the point in time, right? So that's something to keep in mind as we kind of reveal what Cloud Shannon did, who was working for the research lab for AT&T, right? So Shannon shows that there is a true optimal rate, okay, as a function of p. I'll reveal it in a moment, but he gave A, there exists a code that gets this rate, and B, no code can do better, for sufficiently large n and small enough d, delta, and stuff like this. So A, it's very practical, like, okay, there are good codes, let's go find them, things like this. But B, it's like, oh, this looks like a law of physics or something, right? This is like very beautiful. No one thought, or, it was not so clear that there's going to be such a clean theory that comes out of this. So this paper like also opens up a whole field of error correcting codes and stuff like this. Okay, so that's also maybe one thing to keep in mind. So what is this optimal rate? It is, well, I only gave it half the answer. It's 1 minus h of p. Okay, what's h of p? So, oh, that was a rhetorical question, but yeah. So h of p is this entropy quantity, which we'll discuss a little later. P log 1 over p plus 1 minus p log of 1 over 1 minus p. So as delta goes down to 0 and n and m get big, you can't do better than this. Okay, so there's some little o of 1s I'm hiding, but yeah, right? But the idea that there's some kind of limit, universal limit, it's in and of itself, wherever it lies, is already a huge conceptual advance. Right? Imagine something like that coming up for LLMs. That would be unbelievable. Of a bit being flipped. So this is only in the stochastic model. So later on, people study things like, adversarial models. The adversary can flip a p fraction of the bits. Can you handle that? Various other things. So this is only in this one particular initial model, right? Yeah. Yeah, or inverse redundancy because it's a value less than zero. I mean, less than one, between 0 and 1. So m, the numerator is the length of the message you're trying to send, and n is the length of the code. So 1 divided by that is your kind of redundancy overhead. Yeah, so it's really a slightly, yeah, I'll give the more formal one in a version, but it's saying if you want error rates delta, then you can't do better than 1 minus h of p minus delta. So as the error rate goes to 0, it'll approach 1 minus hp. Yeah, so let's see. Here's the more formal version. For all delta greater than 0, there's a coding scheme of transmission rate at least 1 minus hp minus delta, and average error at most delta. Okay? And then on the hardness side, or kind of the impossibility side, any coding scheme with transmission rate better than 1 minus hp plus delta must have average error at least delta. Okay, so as delta goes down to 0, this is approaching 1 minus hp from both sides. Good. So, okay, so let me explain a little bit this notion of entropy. I have a slightly funny presentation to try to interpret what's going on. So, okay, so if I have a random variable, right? If something very common happens, it's not very surprising. If something uncommon happens, it's more surprising. Okay? So I think of this as like the shock. So I'll define S of X to be, so X is a random variable, and it takes on some value little x. And how much am I shocked by? I'm shocked by 1 over the probability of that thing happening. That's how I'm defining shock. And entropy is your expected logarithm of shock. Okay. There's actually some interesting connections. For example, if you wanted to do a Huffman coding scheme for events and you want to do a small average length, the best you can do actually is this bound and things like this. But so okay, so sort of your average logarithmic shock. So for example, for a coin that flips heads was probability p. Was probability p it flips heads, your shocked log of 1 over p. Was 1 minus p, it flips tails, your shock is contribution is log 1 over 1 minus p. Okay, so this is sort of a measure of uncertainty. For example, the most uncertain, hardest to predict coin is 1/2. Right? Anything otherwise, you can just pick the more common one. And indeed, this equation is maximized by p equals 1/2. In general, if you have a discrete random variable with n possibilities, the most random, hardest to predict is the uniform distribution. And the entropy will be maximized by putting the uniform distribution. And then you'll get n terms, each of which is 1 over n log n. And so you'll get log n total entropy for n possible outcomes. Okay. It has some interesting and sort of natural properties. So first there's this notion of conditional entropy. Okay. So you know, you have variables like y conditioned on x, right? And the conditional entropy is defined as, okay, let's look at the expectation over x. X happens, and now there's some remaining entropy of y, the y conditional on x. Okay, the probabilities have changed, the shocks have changed, okay? So we'll take the expectation over x of sort of the expected shock from y, okay? It's a little funny. If you work through it, if we have time, we won't have time for sure today. It might go in the same bin as the Chernoff bound proof. We will show that, for example, so conditional entropy has this nice thing. So h of xy is like the entropy of the joint distribution of x and y. And it's not hard to show, this is just checking, that h of xy is equal to h of x plus h of y given x. Okay. And now this next thing requires Jensen's inequality, also known as AMGM in the right direction. Well, not quite, but it says, okay, so this sort of, so if entropy is a measure of uncertainty, okay, then at some level conditioning on x should only give you some information about y, right? Conditioning should not increase uncertainty. Even if it's independent, then the uncertainty hasn't changed. But if it's dependent, you know a little bit about how y is going to turn out. So indeed, you can show mathematically that the conditional entropy is always at most the entropy by itself. Okay. If I plug that into the previous equation, then I'll get something like h of xy is less than or equal to h of x plus h of y. This is also can be interpreted as, well, overall possible joint distributions of x and y, fixing the margins of y and x separately, the entropy is maximized by the independent one. Okay, the right-hand side represents what the entropy would be if x and y were independent. Okay, so this is also like a basic kind of principle. So really the only thing that, I mean, this thing is just verifying and adding things up. And this is the only thing that takes a little more effort to prove, but it's only a third of a page. Okay, for now we're just going to take it as given. So as a fun application, you can use entropy and these rules to prove this. Okay, so the left-hand side is saying how many subsets of n are there with at most pn elements. Right, n choose 1 plus n choose 2 plus n choose 3. So how many subsets of there are size at most pn? And it says it's at most 2 to the n times hp. Okay. And there's a really cute way, and this is a pretty tight bound if you expand out what hp is. It's a very strong bound. Now, how can we prove this? There's like a cute, entropy proof. Okay, we can take the log of both sides. We will, yeah. So it's also saying that the log of, maybe I can write it semantically, a number of subsets of size at most Pn is less than equal to n HP. And let me give you a clue. This represents the entropy of something. This also represents the entropy of something else, huh? So the right-hand side is sort of the entropy of n independent random variables, each flipping heads with probability p, n independent coins. No, the right-hand side is the entropy of n independent coins being flipped, each of which flip heads with probability p. Because each of those, so that's exactly what the right-hand side is. No, because no, you can flip them and you might not get a subset of size at most Pn. You can get more than average. Not quite. Not quite. Probably not. Huh? Binomial what? NP? Oh, no, that'll be even less. I think. Well, anyway, the answer is no. Um, so if I pick a uniformly random set with at most Pn elements, so out of all the possible sets with at most Pn elements, and I pick one uniformly at random, right? What's the entropy of that? Well, that's the state uniform distribution. So it's going to be log of the number of possibilities, right? And so it's a log of the number of subsets of size at most Pn, right? So if Z as a subset of N is a random set of at most Pn elements, okay, so that means there's a certain, out of all the sets with at most Pn elements, choose one of them uniformly at random, then this quantity is H of Z, okay? So now I'm trying to relate H of Z to the, independent coins, entropy of independent coins. How do I do that? Somewhere we have to justify this less than equal to, right? Yeah. Yeah, let's like yi is equal to 1 uh, if I is in Z and 0 otherwise. Okay? So if I look at the joint distribution, they are dependent on each other. Right? Because I pick a random set and then I look at the set to see if I appeared in it. Okay? But otherwise it's the same. If I gave you the indicator variables y to n, then you know exactly z. If you know z, you know the indicator variables y1 to yn. So they're the same thing. Okay, so we have equality there. Okay, and now what? Right. So entropy is maximized when they're independent, and each of these have heads with probability p. Okay, so you get this really slick proof. Uh, we use this hammer of principle of maximality. Yeah. Uh, yeah, I guess it should be less than equal to. So entropy does go up to, for p is less than, I say p is less than 1/2. Um, it'll go up as it goes to 1/2. So the probability of an element flipping heads is at most p, and yeah, yeah. Okay, good. Anyway, so entropy actually, especially if you hide one or two of the proofs, actually has a certain qualitative, intuitive feel. All right, so I think we should at least be able to do uh, the existence of a code today. YI is saying did element I appear in the set, and there's n different elements. There's subsets of n. Yeah. All right. So with a little bit of practice entropy, let's now try to look at this theorem. So there exists a code with transmission rate at least 1 minus HP minus delta. Okay, an average error at most delta. Okay. Um, okay. Any ideas? How can you get a really good error correcting code? Okay, so I give you X. You have to determine CX. What should CX be? Well, they're all going to be bit strings of length n, so the size is automatic. You just take a 1 point mapping it here. This is the inverse map. That's many to one. That's why you have a ball. But for x, you need to choose a point cx, code word for x. Yeah. So okay, yes, but I think you're thinking about the inverse map. So it is true that once I decide what the code word for x should be, I should maybe make some kind of Voronoi diagram in the coding space to map backwards. Like if I have some arbitrary point in this space, let me just find the nearest code word and map it back. So that's the natural way to do decoding. We will decode that way, but the question is, what's your encoding? What's your clever scheme? With small redundancy, right? That's going to be kind of pretty robust to Hamming error and stuff. Uh, yeah, sure. P. We'll get to choose N as well. But any ideas? Yeah. Okay. So this is like a parity check. Yeah, yeah. So things like, check some kind of ideas, or even like if you take the SHA or something of your message and write it down, then you can try to check. So this way you can at least check if your message was corrupted. Um, but that's still in a good space of ideas. But yeah, yeah. Okay, so that's what Shannon proposed. And this was a very uncommon style of thinking at the time. We're gonna let n be sufficiently large, and m, I wrote this down wrong, is going to be 1 minus HP minus delta times n. I wrote that down wrong. Okay, so m is the smaller one, so n's a little bit bigger. And then we'll just make n big enough to make our proofs work nice. We'll see where. So we're just going to use a uniformly random function. Okay, and then decoding is going to be exactly the intuitive thing. It's just like, okay, I'm here. Let me find the closest code word, map it back. Okay, we're going to analyze this. Okay, so here are two claims. So first of all, entropy is a continuous function. Okay, so I can choose epsilon greater than 0, but small enough so that the entropy of 1 plus epsilon p minus entropy of p is at most delta over 2. It's some function of delta and p, but I don't really care. Good. Now here's two claims. All right, so I'm going to fix some point x first. Okay. The first claim is that, so I've already have a random thing, right? With pretty good probability, I'm not going to flip that many bits when I send a message, when I send x. Okay. And the second claim is that also with pretty good probability, no other point is going to be this close to my code word for x. Okay, in which case I'll recover x, right? Because x is in that nearby region, and it's the only point in that nearby region. Okay, so, or actually, let me mix it. Yeah. Okay, good. Okay, so, okay, now, suppose these claims are true. Okay. I just want to make sure I don't mess this up. Okay. Okay, so if these claims are true, then by the union bound, both of them will occur with probability of error at most delta, because you have delta over 2 for both. And when both of those do occur, you're going to correctly recover your message. Okay, so that tells us that, now this is a little bit tricky, the probability over the random choice of x, the random choice of c, and the random choice of noise, the probability that I do not decode my original message is at most delta. Okay? I mean, I'm just taking the union bound. Now, this seems kind of good, right? But it's not exactly what we're looking for. What's faulty about this? It's the C. So this is averaging over all choices of C, all choices of X, all choices of noise, right? Because that second statement is about whether or not there's other code words that are nearby. Okay, so those two statements above are randomized over C. Okay, so right now we have a statement that's randomized over C. So on average, over all errors, over all X, over all noise, we get small error. But what we want is much more ambitious, right? I want a single code with low average error. Yeah. X and N for a single C. Here I'm saying, oh, if you pick a random C and a random noise and a random X and we apply our encoding decoding, you'll recover it with probability 1 minus delta. But what we really want is one code that you can put into the telephone system and it'll get this error. This is the best part of the proof. Where's that code? Okay, so I can write this as the expected value over C, the probability over X N, D N C X is not equal to X is less than equal to delta. So that's fine just because I'm rewriting that first statement. Good, that's a good step. Now what? Yeah. So this says that the average overall codes of its average error is at most delta. Average appears twice, which is a little confusing. But the average overall codes, the average error is at most delta. Okay. So that means there exists a code where the average error is at most delta. Yeah. Well, I guess, yeah, so what's one way to get a good code then? Well, I guess if you're willing to like increase the error a little bit, you can at least use Markov's inequality. If you pick a random code with probability 1/2. So this is actually a real thing. Now another thing is that a random code is very hard to write down compactly, right? It's not like a hash function like we had before. So this is actually a major issue for the next 50 years, right? Roughly trying to de-randomize this construction, but even the existence of a code, right? And then maybe if M and N aren't too big, you'll just write down the whole table, right? And just save it in ROM or something. Not even RAM, ROM, because you'll never have to change it. Okay. No, now we do, if I'm not mistaken. Yeah, we've come a long way, including stuff using expander graphs, which is pretty cool. That we'll talk about later. Okay, but this is the start of a field, not the end. Although Turing, yeah, kind of left and went on and did other things soon after. Okay, don't worry about that. It's not important. Okay, so we have these two claims. This one's actually relatively easy. Um, the claim is that for some x, I encode it, I flip some bits, I flip at most 1 plus epsilon pn bits for n sufficiently large. Why? Sorry? I don't know what Bernstein is. Chernoff, right? So you expect to flip pn bits. The odds of getting epsilon pn bits is going to be like e to the negative epsilon squared pn or something. I'll just make n big. This goes to 0. Okay. This part's not very interesting. This part, is this going to just like stay there? Okay. Yeah. For me, the goal of a faculty meeting is to eat. I just like bring food and I just eat. And I make sarcastic remarks and confuse the elderly. Okay. All right, here's a more interesting one. Was probability 1 minus delta over 2. No other point x prime in 0, 1 to the m has cx prime minus ncx less than or equal to 1 plus epsilon pn. Now here I'll note that you could apply Chernoff. Or no, you could. No, that's not true actually. Okay. So ncx is first you chose some random thing and then you flip some bits. So you can fix that, and now it's just a fixed point in space, and the remaining randomness is cx prime. Right? So it's really saying, okay, The odds of some other point being within 1 plus epsilon Pn is pretty small for this choice of m and n. Okay. So, okay. So I'm going to call this y, so I don't have to write it again. And we're going to condition on y. So all the randomness left is on Cx. For any particular y, we'll show this is true, but this is true for all y. Okay, so now Cx prime is chosen uniformly at random among all sets of size 2n, right? I mean of size. So, okay. So the odds of being in this small region around y, okay, it's going to be the total number of sets, right, that flip at most at 1 plus epsilon Pn bits in y, divided by the total space of code words I could choose. Okay, so this is where we're going to use entropy for like the first and only time. Extra parentheses, 1 plus epsilon p minus 1 n. Okay, maybe the parentheses balance and maybe they don't. I think they balance. Okay, so that's the probability, and by the union bound, the probability that any of these fail, okay, is we're going to multiply this by 2 to the m, because there's m bits on the input size, so there's 2 to the m possible input messages. Okay, so by the union bound, you're given something like 2 to the m plus h of 1 plus epsilon p minus 1 times n. Okay, and you want this to be at most delta over 2. Okay, so when you start taking the logs on both sides and you rearrange, you're going to get that m needs to be at most 1 minus h of 1 plus epsilon p balance parentheses n. Wait, is that balanced correctly? No, there's one more parentheses. Okay, minus 1 minus log of 1 over delta. So I promise all I did was take the log of both sides and rearrange some stuff. Nothing special happened. I'm getting a headache. Okay. What happened to what? It was never inside entropy. Yeah. See, h of 1 plus epsilon times p. Maybe I should, yeah. Okay. What if I said, p tilde is equal to 1 plus epsilon p? This is going to be a big breakthrough. Okay. The issue is just the representation. This is what we learned from ML. Okay. So I'll call these p tildes, right? I often feel like the hardest thing about half of what we do is like, I don't know. I remember I took this like differential equations class in college, and like I would always make, you guys have, maybe some of you have taken differential equations before. So my experience is that you write these really long equations, and I realized the only reason I ever made a mistake is that I couldn't fit an equation on one line, and I would line wrap, and I'd always introduce some error there, and I'd get a mistake overall. And so I was like really struggling. And then I eventually figured out my problem or solution. You know what I did? I did a landscape. And I never made another mistake for like the rest of the semester because I could fit it on one line. And I feel like this is often the case of our hardest problems. Okay, so once you balance parentheses, I think this is correct. Now I've lost my place. Okay, um, so this is why we chose M as we did. Well, actually, in a moment. Now, we chose epsilon small enough uh, so that the difference between HP and H tilde P is at most delta over 2 or something like this. Um, so this is less than equal to 1 minus HP plus delta n minus 1 minus log of 1 over delta. So M needs to be smaller than this relative to, I guess, minus, not plus. Smaller than this relative to n in order to be able to take the union bound we want to get the claim we want. Okay, so these terms are negligible as n gets big, and so this is exactly the transmission rate that was claimed. So now you're going to make m as big as possible. So yeah. Yes, yeah. Sorry, that is greater than what? Yeah. Yeah, okay, you actually set M to be this, the full underline, including the parts that aren't underlined. Yeah, so you'll set it to this, which is basically this, minus some little o of 1 term. So for n sufficiently large, uh, this will get swallowed up by this. So I could have made delta slightly smaller to begin with or something, and it would have been okay, yeah, that kind of thing. I cleaned it up a little bit to make the theorem a little bit less painful. So otherwise you just make m as big as possible. You're allowed to make n as big as you want. So m and n are going to be pretty big to get, to start approaching this rate. So you're not sending like 1 bit at a time. You're going to be sending larger messages at a time, which will result in larger tables for your random code. So there's, other issues going on, but at least, asymptotically in mn and delta, you're getting the right thing. So that's the first part. One can also show way over time a lower bound to show that this is basically correct, especially as delta goes down to 0. I don't know if you guys want to see a lower bound or not. We can do something else that's fun and different. I can do this for the first 10 minutes when we come back. It's sort of similar style of thinking, some kind of Chernoff bound and thing like this. Otherwise, I can leave this to you to read in the notes. By which I mean probably very few of you will read it very slowly, but it's okay. We did the most important part, which is that the random code is an optimal code, and then you can check this on yourself to believe that it's tight. So okay, I'll make up my mind whether or not we want it. My worry is that over spring break we're going to lose a little bit of interest in seeing the other side of this, and maybe it's an okay time to just start something new for fun. Okay, but one can prove the other side as well. Okay, I'll end it there. Sorry I went over. Thank you.